Hello, physics students. I am Mr. Williams, and we're going to talk about magnetism. Magnetism is a phenomena in the universe that gets very little credit, but yet it does so much for us as a world. Um, Magnets have everything to do with, let's see, the Earth's magnetic field, how a compass works. It has to do with your ceiling fan would not work without magnets. Anything that has a motor requires magnets. Now, anything that generates electricity, except for solar panels, that's a little bit different story. But like all the electricity that we use to be generated requires magnets. And so we're going to be talking that over the course of the next few weeks. Now, this lecture, we're going to talk about magnetism in general and the very, very basic fundamentals, okay? So let's get started. So magnets, they can be found naturally occurring, and it is from a material called magnetite. So magnetite is a naturally occurring magnetic material. It's basically, it's a rock that you can find. Magnetism, the definition of that, it would refer to the properties and interactions of magnets. So how do magnets behave and interact with each other and other materials? The magnets can exert a force on other magnets. Okay, we'll learn that a north and south pole of a magnet, they attract, and north and a north will repel, and a south will repel. The ends of magnets can be attractive or repulsive, just like I said, and the strength of the magnetic force increases as the magnets move closer together. So as they get close together, they're more likely snap together or push apart, depending on which end's facing which. And of course, the converse of that is the strength of the magnetic force decreases as the magnets move further apart. Okay? So a magnet is surrounded by a magnetic field. And a magnetic field is a region surrounding the magnetic material where the magnetic force acts. Okay, so the field is the region where there is magnetic force. Okay, magnetic field lines, they're a little bit different. So magnetic fields, they're represented by magnetic field lines. Magnetic field lines have a direction that go from the north to the south pole. So they represent the magnetic field. And so we would draw, for example, the magnetic field by using magnetic field lines, and it goes from north to south. Magnetic poles. So all magnets have a north and south pole, and they're located at opposite ends of the magnet. It doesn't matter what shape of the magnet is. It could be a U-shaped magnet, as you see at the top. It could be a cylinder-shaped magnet, as you see at the bottom, or it could even be one of those spherical magnets, the little magnets that are in the shape of a ball. They still have a north and south pole. And so the definition of a magnetic pole is the region where a magnetic force exerted by a magnet is the strongest. So the North Pole and the South Pole is the strongest part of the magnet. And here's something important to know. The magnetic field lines, they always connect the North and South Pole, okay? Always, there's always a connection. So hopefully you already know this. When you have two magnets, they have a north and south pole, and two north poles or two south poles, they will repel, they will push each other away. That's important because we can use that in engineering to manipulate devices to push away when we want it to push away. We can also manipulate devices by using north and south poles that when they come in contact with each other, that they would attract. So opposite of poles attract, as you see in the top of image, opposite poles attract, and in the below you see that same poles will repel. And so we can design devices with magnets that alternate north and south poles, and we can cause that. And we'll see that later in the next section, how if we combine something called electromagnet with alternating north and south pole magnets, we can generate motion. Awesome. That's how a ceiling fan would work, for example. All motors work that way. So, like we said, magnetic fields have direction. Okay. And so, if you took a compass and you put a compass near a magnet, the magnetic force would cause a compass needle to rotate. Okay. And a compass needle rotates until it's lined up with the magnetic field lines. And so, if you have a compass and you take it out, you'll notice that it always points, it always points to the magnetic north pole of the earth because the earth has a magnetic field. And you could, in comparison, if you took like a bar magnet and put it close um, to the compass, you could see the compass like rotate if you just rotated the magnet around the compass. Like we said, Earth has a magnetic field. Earth acts like a giant bar magnet and is surrounded by a magnetic field. A compass needle will point north because it aligns with Earth's magnetic field. Okay, so there's something that we're going to have to be careful to understand. So if you have a compass and the compass will point towards the North Pole, we have to think about how, well, we know that north is attracted by an opposite magnetic pole. All right, north is attracted by south. So we have two things that we got to think about: the north geographic pole, and so that's north on the map, would be the north geographic, okay, north on the map. And then there's the south magnetic pole. Well, magnetically, what we call the North Pole, where people pretend that Santa Claus lives, where we have the North Pole, the South Pole, the South Magnetic Pole, is in that North Pole geographic region. Okay, so like where the Arctic is, above North America and Asia. Right, as you go north, that is the South Magnetic Pole because a compass needle will point to geographic north because that north compass needle is attracted to the south magnetic pole. Okay, and I'm going to go over that again right here. So the north pole of a magnet is determined by the end of the magnet that points geographic north. The magnetic north of a compass needle is being attracted by the south magnetic pole. That means North Pole of the Earth behaves like a South Pole magnet. Okay, so no one knows exactly what produces Earth's magnetic field. Okay, the prevailing theory is that the circulation of hot liquid iron in Earth's outer core produces Earth's magnetic field lines. Okay, or excuse me, Earth's magnetic field. And so, of course, we've never been to the center of the Earth. Last semester, we talked about how we use waves to map and infer and use earthquake waves to come up with a model of what's inside the Earth. We don't really know. This is our best understanding. Okay, so that's all we're going to cover for this lecture. Be prepared for another lecture coming up, and we will talk a little bit more about what's on the interior of a magnet and what makes a magnetic material actually behave like a magnet. Okay, guys, come to class. Ask me any questions that you have during class or in those private messages. Take care. Have a nice day.